So here the question is, so that the displacement current in a parallel plate capacitor is equal to the conduction current in the connecting leads. Okay, so for parallel plate capacitor, if we take this is a parallel plate capacitor having area A, okay, and then uh, on this plate plus q charge is accumulated and minus q charge accumulated here. So the electric field from top plate to down plate is defined as E equals to sigma divided by epsilon naught, where sigma is called surface charge density. Okay, so surface charge density, that means charge per unit area, per unit surface area, that is q divided by a. Therefore we get E equals to q divided by a into epsilon naught. Okay, now uh, from Gauss law we can write the electric flux phi E is nothing but surface integral of E dot ds. Okay, so since the surface area vector is perpendicular to the surface, okay, and the electric field also perpendicular to the surface, so therefore E dot ds will be E into ds. Okay, so E is constant here, so E ds, area is a here, so E into a. Okay, so therefore we get E into a, that means q by epsilon naught. So here we get the flux is nothing but q divided by epsilon naught. Okay, okay, now again from uh, Ampere's law, after Maxwell correction we get the line integral of magnetic field B dot dl is nothing but mu naught times I C conduction current plus I D, that is called the displacement current. Okay, so here the expression of displacement current is mu naught times IC plus epsilon naught into del phi E divided by del T, del phi E del T. Okay, so this is the expression of Maxwell's Ampere's law after Maxwell correction. Okay, now in between these two plates there is no conduction current. Okay, in between these two plates there is only a dielectric medium which is insulator. Okay, types of insulator, so they cannot conduct current. Okay, there will be no conduction current, so therefore IC will be 0. Okay, so ID here is defined as epsilon naught into del phi E divided by del T. Okay, equals to epsilon naught into del T of what is phi here? Phi here q by epsilon naught. So epsilon naught is constant here, so basically del q by del T. So del q by del T is the current IC, conduction current basically, through the connecting leads. So here connecting leads means the wire which is connecting the capacitor to the external circuit. Basically if you can take a battery which is connected with this capacitor, then this wire is called connecting leads. Okay, so here q is dq by dt is the current flowing through these leads, current flowing through these connecting wires. Okay, so this is the I conduction through leads. Okay, so proved, we can prove that is ID, displacement current, is nothing but the conduction current in the connecting leads. Okay, now next question, an electromagnetic wave is propagating from one linear dielectric medium to another another with no free charge, no current. That means you can take if jf is 0 and also sigma f is 0. Okay, write the boundary condition for the uh, electric and magnetic fields. Okay, so this is a common question. We shall not solve here. You can find it any standard book. Okay, so let's move to the next question. So for a plane electromagnetic wave propagating in a source free region, now so that the Maxwell's equations reduced to k cross E equals to omega b, k dot b is 0, k dot E is 0, where k is a wave vector, E and B are the electric field and magnetic field respectively, omega is the frequency of the wave. A very easy question. So let's take the electric field in terms of this E naught x e to the power iota k dot r minus omega t, where k is given as wave vector and omega is the frequency. Similarly, we can take the magnetic field as b naught e to the power iota k dot r minus omega t. Okay, now from the first Maxwell's law, that is basically divergence E equals to what? Divergence E equals to rho by epsilon naught. Now since the wave is propagating through a surface free region, that means here rho will be 0, also j will be 0. Okay, so here rho will be 0, that means divergence E will be 0. So divergence E will be 0. So here divergence is basically uh, a operator, but in general form it is a differentiator operator. Means it differentiate the another vector. Okay, depends on a function of position only, x y z. Okay, so if we operate this divergence operator to electric field, then it affect only the position coordinate of that field. Okay, so here position coordinate is k dot r. So therefore we get from here we get divergence E equals to 0. After that, if we operate this on this, then we get only k vector is constant here, k dot r is here. So therefore we get k dot E equals to 0. So k dot E equals to 0 we get. Similarly, if we use the second Maxwell's equation, that is divergence B is 0, and then again if we differentiate, then we get k dot B equals to 0. From here we can write k dot H equals to 0. Okay, so k dot E equals to 0 and k dot H is 0 already here. Now for the second one, that is k cross E equals to omega b. Okay, next again take the third Maxwell's equation, that is curl E equals to minus del b by del t. Okay, similarly divergence is a position operator. Basically it is a function of position only, so it operates E and then extract only the position part. Okay, so that therefore we get from here we get iota times k cross E. Okay, and here minus del b del t. So it is a time operate on time variable only. So from here we get minus iota omega, and what we get from here minus iota omega, then again b. Okay, again b vector minus iota omega, and then again b vector. Also there is a term I think. Okay, okay. So here curl E is nothing but basically k cross E. K cross E is nothing but minus. There is a minus already. Okay, so it will be plus. Ultimately minus into minus will be plus. So we get k cross E equals to omega into b vector. So we can find all this relation. Okay, that is k dot E equals to 0 here, k dot B is basically k dot H is 0, k dot B is 0 here, and also k cross E is omega times B vector. Okay, so